Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be continuing our discussion about linear momentum by discussing a new conservation law, namely the conservation of linear momentum. Now, I've referenced this conservation law in a previous video, namely my video about Newton's laws of forces, or Newton's force laws, and linear momentum. Today we want to look a little bit more at conservation of linear momentum as such. We can begin by recalling a few things discussed in previous videos, namely that we have defined linear momentum p as the mass of an object times its velocity. And then the other thing is that we might want to recall is that Newton's force laws govern linear momentum, namely that force imparts impulse, and so if you have a net force acting on an object, then that will be the essentially rate of impulse. So that would be delta P over delta T, and that for each force there is a sort of reaction force, that's Newton's third law, which ultimately means that you end up with conservation of linear momentum. Each force has an opposite direction equal magnitude reaction force, implies that each time that you impart momentum to one object, momentum is also imparted, or impulse is also imparted to another object, but in the opposite direction, but an equal amount of impulse. This implies the conservation of linear momentum for a closed system. So basically the summary of what these things are saying is that for a closed system, the sum of momenta at the start and the sum of momenta at the end must be equal. This is the conservation of linear momentum. So what defines a closed system? Well, it's basically any system for which there are no external forces that can act upon the system. All right, so as long as you don't have any external forces acting upon your system, you have what is called a closed system. So with that said, let's consider how might we use this. Now, the most common use for this in physics problems, at least in an introductory course, is various collisions. And I will discuss those in a different set of videos, and the reason for that is that if you are following along in order, these videos kind of will be self-contained, albeit if you're following along via a textbook, some authors like to introduce linear momentum first and others like to introduce energy first. And collisions mostly require that you've covered both of these topics. So I'm not going to go into types of collision here because of that. I will, however, do some very simple ideas with collisions or exchanges, namely by saying we have a collision and here's the initial conditions and here's the final condition of one object, so what's the final condition of the other? You can do all that just using linear momentum, assuming a closed system. You can do more than that if you also understand energy and know whether it's an elastic collision or a perfectly inelastic collision, etc. So let's consider simple case. So simplest case, maybe you have like two people who are ice skating. So they are kind of like out on the ice with their skates, and they are standing together and they push off from each other. So this guy and this gal kind of like push off from each other while skating on the ice. And the result of that is that one of them ends up going this way and the other ends up going that way. And if they're initially at rest, then that means that the entire system has some initial momentum of 0. So initially at rest means that the sum of initial momentum, pi, is 0. Conservation of linear momentum implies that our final linear momentum must also be 0. So therefore, if we know what the two masses are, maybe this guy has m1, this gal has m2, then we know that m1 v1 final plus m2 v2 final must equal 0. And so that means that we can figure out the ratio of the two final speeds. We can either express this as like v1 final over v2 final. And note that this is, now I've converted from velocities to speeds. We know that they're going in opposite directions, so we know that v1 is negative of something v2. But this ratio, v1 over v2, will look like m2 over m1. The ratio of their speeds will be equal to the inverse of the ratio of their masses. Or put differently, v2 final as a velocity will look like negative m1 over m2 v1 final as a velocity. Okay, so that's a very simple use of linear momentum conservation. And note that we were able to do all that without any kind of collision, energy conservation, anything like that. Another use of this, again, that doesn't require knowing anything about energy, would be something like you have a firework. So we shoot off this firework, right? And it kind of launches off into the air. Eventually it runs out of fuel. Somewhere up here it explodes. Okay, so the exploded firework ends up falling into multiple pieces. So here we kind of boom. Maybe it's a dud, so maybe it just kind of like breaks into two pieces up here at the top. Well, where are these two pieces going to land? Well, one piece may be ejected kind of forward and the other piece ejected kind of backwards relative to the actual motion. And so one piece could land here, the other piece could land here. And we might ask, like, where are these two locations? And the answer is that there is a thing called the center of mass for the system. So I'll just label this center mass. And up here, there's a thing called center of mass for the system. And that center of mass for the system actually just continues along the same parabolic trajectory that this thing had when it first exploded. So center of mass has to land somewhere in here. And we can figure out where the other two pieces must have landed if we know some piece of information like where was it when this happened and how much mass does each of the two pieces have, and maybe, conditions for one of the two pieces. Put differently, if I know the two masses and I know what the initial conditions are here and I know where one of them landed, then I can figure out where the other one must have landed as well. Now I've introduced a new concept here called center of mass. Basically the center of mass location is given by, to use kind of a pun, it's kind of like a weighted average. It basically means add together the mass of each piece and where that piece is located, and then divide by the total mass of your object, and now you have the center of mass. So algebraically, that basically looks like the sum of the individual mass pieces times their respective locations divided by the sum of the total mass. So this would look like m1 x1 plus m2 x2 plus, and however many pieces you have, divided by m1 plus m2 plus m3, etc. However many pieces of mass you have. And again, I would like to maybe address this specific problem in a future video without necessarily addressing it in depth in this one. This is meant to be kind of like a short overview type. Okay, third kind of problem is where you have collisions and let's say, all of the initial conditions and one of the final conditions, or maybe all the final conditions and one of the initial conditions. So maybe I have a couple of cars, and one of them runs the red light, right? And so one of them crashes into the other vehicle. This is a complicated collision because it might be in more than one dimension. So something like this could happen, where you've got one car crashing into the other. And in this case, looked at from above, you have one object moving like this, and you have another object moving like this during the collision. And maybe the two stick together, for example, and so the net motion after the collision maybe comes off in this direction. And so if we know that the two are stuck together and we know what this guy's initial conditions are, then we could figure out what this guy's initial conditions must have been as well. And so if you're doing like a police report or whatever from a car crash, you can figure out, did this guy run the red light? Was he speeding? That kind of thing during the collision. A simpler version of that would be, I have one ball and it collides with a second ball, so M1, M2. And then afterwards, I now know what M1 is, and I don't know what M2 is. So I know V initial 1, I know V initial 2, I know V final 1, and I don't know V final 2. And so if that's the case, I could use momentum conservation to solve for this guy by saying M1 V1 initial, or V initial 1, plus M2 V initial 2, which we established was 0, is equal to M1 final V final 1 plus M2 V final 2. And that's conservation of linear momentum. All right, so I have a quick example, well, somewhat of a quick example for conservation of linear momentum. We have a 3,000 kilogram asteroid and a 45,000 kilogram asteroid. The larger asteroid's initially at rest. Put differently, we're kind of viewing all this from the inertial frame of the larger asteroid at the beginning before the collision. So maybe we're like in a spaceship or a probe or something that's kind of hovering near the second asteroid and totally matched its velocity. So it looks like it's got a 0 velocity. And this smaller asteroid comes hurtling in at 10,000 meters per second, crashes into the bigger asteroid so that the two are embedded together and moving off in some direction. And what we want to know is that, given that they are stuck together and therefore have the same final velocity, we want to know what the magnitude of that velocity is. We don't know what the actual direction is because it's not specified in the problem, nor does it need to be. But we want to know what's the speed that the two have together at the end. So conservation of linear momentum basically says m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. And what this translates into in terms of the problems we have here, this guy is 0, and this are equal. v1 final equals v2 final. We'll just call that v final. Okay, and v initial is just v initial. So we can translate this entire problem to m1 v1 initial is m1 v final plus m2 v final. And that in turn is just m1 plus m2 times v final. It follows that v final must be m1 divided by m1 plus m2 v initial. So that is 3,000 kilograms divided by 3,000 plus 45,000 kilograms times 10,000 meters per second. That you can plug into your calculator to get a final speed of about 625 meters per second. Maybe, depending on how many significant figures you have, you can retain all 3 of these digits. And that's it. That's a conservation of linear momentum problem, or a simple conservation of linear momentum problem. So that's all that we're going to do in today's video. Hopefully you've learned a little bit about this topic, and thanks for watching.